Hi all, welcome to the fifth part of the video lecture on complexity theory. So in the previous video lectures, we gone through different complexity classes like class B, NB, and we gone through some of the terminologies related to it. Okay, and we formally define what is class B, NB like that. And now it's time. So in between not only that, last video lecture we discussed that NB hardness. So what kind of problem you can call as an NB hard problem, and what about NB completeness? I just given you a feel about it, and we saw that the basics behind all this process is something known as reduction. I mean, from one difficult problem, are we able to move or reduce to some other difficult problems? So both are difficult, so that's the thing. But if you want, you can do this reduction between any problem, whether it is difficult or not. But basically we are interested on the reduction between two difficult problems. Okay, and how this reduction can be done? The basic thing is the time spent for this reduction should be polynomial, otherwise we will not get any benefit. Okay, we already saw why it is so. Okay, so what kind of benefit we are getting if we have a polynomial reduction between two difficult problems? And I already told you many people come up with many reduction, and we have the very first problem to which all other NB problems are reduced, and that is the first NB hard as well as NB complete problem. So given by Cook and Levin, and that makes this basis for the complexity theory. Okay, now to give you, in this video I'll try to explain this reduction through using some random problems, say from graph theory. And so before that, let me ask you, so hope you are familiar with this problem like clique and independent set. So what is a clique basically? So I will take an example and tell you. So I am just drawing on graph here. Okay, let me draw and come back. See, here I randomly drawn two graphs. So this is a given graph, say with the 5 vertices v1, v2, v3, v5, v4 and v5, and you can see the edges like. And now I have a complement graph at the other side. So let me just ask you, what is a graph complement? You might study it in your graph theory classes. So just like a complement of a set and all. So basically when it comes to set, the complement is universal set minus given set. So something like that. Here when it comes to graph, the universal graph is something like a complete graph having all possible edges between every pair of vertices. As you know, this G is not a complete graph, right? So in the complement, we will get elements which are from the universal graph but not from the given graph, like that. So complement, the elements are not complement of a set means the elements of the set will not be there in the complement, but those elements which are there in the universal set but not there in the given set will be there in the complement. It's similar concept. So here, you know, if you are looking at this v1, v2, v3, v4, where every pair of vertices are connected to each other, and those pair of vertices become disconnected here, because all these edges you can't include in the complement, right? Now if you are looking at v5 is connected to v2 as well as v4 in the given graph. So when it comes to the complement, the remaining edges will be added, say v1 to v5. So let me take a different color. See, if you are looking at v1 to v5, this particular edge is not here, right? So this particular edge is absent here. And similarly, another possibility is this particular edge. Only these two, right? Because if you are adding these two more edges, you will be getting something like a k5 as this one, because everybody is connected to each other. So the complete equivalent or the universal graph corresponding to the given graph is actually k5. So what we done is we added those edges which are there in k5 but not in the given graph. Okay, so let me remove them. So you can add one more edge, say this one. So this will complete the or this will form the complement of the given graph. Hope it is clear. So what you have to do is, so those edges which are there in the given graph you remove, that will not be there in the complement graph, and those edges which are not there in the given graph and which are there in the equivalent universal graph, and that is nothing but the complete graph corresponding to 5 vertices, say in this example, say k5. So you know, these two that magenta, that color edges are not there in the given graph but they are there in the universal graph, that I added for finding the complement. So let it be there as it is. Now let's see two independent different graph theoretic concepts. The first one is clique. So what is a clique? So the definition you can see, it is a maximal complete subgraph of a given graph, and what we are interested is maximum clique. So here we have two terminology, maximal as well as maximum. Let me tell you the difference first. So maximum, always it says that it is with respect to cardinality. Okay, with respect to cardinality, we are cardinality. Okay, we are defining the term maximum in the sense we are interested on the clique having maximum cardinality, in the sense the maximum number of vertices as part of the clique. So what is clique we will see, and maximal in the sense none of its superset should possess that property. So what is the requirement for a clique? I am finding a subgraph having that property and none of its superset is having this same property, then I can say that this is maximal. Similarly, we have a minimum as well as minimal. Minimum means the minimum cardinality, just count the number of vertices participating in it, okay, when it comes to graph. Minimal means none of its subset should possess that property. Okay, something like that. Anyway, keep that in mind. So what is a clique? Clique is a maximal complete subgraph of a given graph. So basically clique means it is a maximal, means none of its superset should possess that property. And what is that property? Complete subgraph. So complete, you know, everybody is connected to each other. So the given graph itself is complete. For example, if K5 is given instead of this graph, I can say that that itself is a clique. Okay, but unfortunately the given graph is not a complete graph. So what is the maximal complete subgraph of the given graph? So you can see that what we need is complete, right? So if we are looking at a triangle, say between v1, v2, v3, you can see that this is a complete graph because all the vertices pairs are connected, right? So this is a complete graph, fine, but it is not maximal in the sense some of its superset. For example, if I add this v4 also, this v1, v2, v3, v4 together is also forming a clique, in the sense everybody is connected to each other, fine. Okay, so in the given graph I made it little confusing, but you can see that focus on that green color edges. Okay, you can see that itself is a clique, in the sense complete. So what we are interested is maximal complete subgraph, in the sense that triangle is complete, at the same time that square kind of thing, the K4 is also there, so K4 is a superset there, so that only going to act as the clique, particularly maximal clique. By default, if I am using the term clique, it means maximal. Okay, so here you can see that this is a clique, this is a maximal clique. Okay, fine. And now let me tell you another clique also. This is also a clique, fine, because none of its superset, because if I am focusing on vertices v2, v4, v5, it form a triangle, says that every vertex is connected to each other, it is complete, and none of its superset is having this property, in the sense superset is the sense if you add v1 the clique property is violated, if you add v3 the clique property is violated, if you add v1 v3 together, that time also the clique property is violated for the subset v2 v4 v5. Okay, so here you can see two maximal cliques, right, or maximal clique, in the sense maximal complete subgraphs, and out of them which is having the largest cardinality. For example, v1, v2, v3, v4, I have 4 vertices and I have a K4 as a maximal clique, and v2, v4, v5, I have a K3 as a maximal clique. So here you can see the subgraph K4, and here you can see the subgraph K3, and both are found to be cliques because they are complete as well as maximal, in the sense none of its superset is having that property. Clear? Now what is maximum clique? Maximum clique, the one with the maximum cardinality, so that is only K4. So for the given graph, K4 is going to act as a maximum clique. Okay, yeah, that about it. So I can say in our example the maximum clique is what? Maximum. Now I am writing maximum, so that is what we are interested for a given graph as a whole. There may be more than one also, but in our graph there is only one with the maximum cardinality, only one clique with the maximum cardinality, and that is v1, v2, v3, v4. Fine. Now what about independent sets? Similarly, so keep that in mind. So why I taken the graph and its complement, that is for a different reason. I just wanted to tell you the reduction for that purpose. So now you take this complement graph as a different graph which we are interested. So a graph can be like this also, right? So don't look at the relation between G and G complement, let it be there, that I will tell you at the end. So this G complement, you treat it as a new graph given to you, and you are asked to find out something called as independent set. So as the name says, independent, I have a set of or subset of vertices. So basically we are interested on a subset of vertices which are independent in the sense there is no common edge between them. So it is just opposite to the clique problem. Clique, I want the subset of vertices which are connected each other. Between every pair of vertices there should be an edge, but here I need a subset of vertices which are completely independent set. Independent, I mean there is no common edge between them. So if you take any two pair of vertices, there is no edge, so that you should ensure. Okay, so similarly here also you can think about the maximal independent set and maximum. So basically we are interested on max independent set in the sense the one with the maximum cardinality. Can you tell me what is the independent set in this particular graph? You can see if you are looking at v1 alone, that is independent because there is only one vertex and it is not connected to any others. Okay, so this is an independent set. Okay, now let me tell you another independent set, the v3 and v4 together. It is an independent set because there is no common edge between them. Okay, now let me tell you a third independent set. If you want, you can take this v1, v2, v3. See, there is no edge between them. There is no edge between v1, v3. There is no edge between v1, v2, and there is no edge between v2 and v3. So it is also an independent set. Now what we are interested is, we are interested on maximum clique, the one with the, so can I have a bigger independent set than this? So you can think about that way. So here you can see that if you are focusing on this 4 vertices, okay, it is going to form an independent set, right? So maximum independent v1, v2, v3, v4. Okay, so the maximum independent set of the given graph is found to be v1, v2, v3, v4, because there is no edge between any pair of vertices in this set. v1, v2 no edge, v1, v3 no edge, v1, v4 no edge. Okay, similarly v2, v1, so that is a checking part actually. v2, v3 no edge, v2, v4 no edge, like that. Now if you add v5, I can't call it as an independent set because v5 is actually paired with the v1 and all. Okay, so this set you can't increase further. So this is a maximum independent set possible. Hope the concept is clear. Okay, so these are these two terminology you are supposed to study already as part of graph theory. Anyway, I explained again because I don't know how much terminologies you are familiar. Okay, so that's all. Now my intention here is to show you the reduction, right? So so before that, let me tell you the difficulty of these two problems. So whether it is clique or independent set, both are NP. NB, as we already know, non-deterministic polynomial time, right? So both are, there is no deterministic polynomial time available for these two problems as of now. So there are many such problems. We saw many, and we will add more problems also in future. Okay, so this clique, given any random graph, say you don't think about a small graph like this, you have to think about a graph of say million vertices and that many edges. Can you find out the maximum clique? So that is an interesting problem, right? So see, all these problems, they have some applications also in the background. Let me tell you on quick application of this clique. It is something like so you can visualize your Facebook or some social media platform, and the how people are connected to each other, so that you can visualize as a graph. So the people in your Facebook, let them be the vertices, and if two people are friends of each other, you can connect those vertices, corresponding vertices, with an edge. So you are basically getting a friendship graph on the background, right? Now what we are interested to find is this clique. Okay, whether it is maximum or maximal, both are fine. So we can always try to find out the maximal cliques here and there. So in case of Facebook, that will be finding application. And sometimes, okay, maximum is also having application. So if you are finding out maximal cliques, you know, inside that clique, say 1000 people are there, that says everybody is connected to each other, everybody is friends of someone else. Okay, so if you want to communicate some advertisement and all, you don't have to share that with all these 1000 people. It's enough to give that ad to one representative person. Okay, so definitely when other people are friends of him, so from him it will be delivered to others. So something like that. I was just trying to find an application. So similarly, you can find this, because most of the application, real world application, you can visualize as a graph on the background, and you can try to solve certain graph theoretic problems like this, and that is going to give solution to the original problem you are having on the background. Similarly, you can think about some application of independent sets. There are many, you can Google it. Anyway, I was trying to say, so that is the kind of problem we are having. We have a very complex graph, say with millions of vertices and edges, and you are supposed to find out what is the maximum click. So if it is an order of n algorithm or n square algorithm, we are very happy because a million vertices we are having, n in the sense number of vertices, so order of n itself is order of million, but still it is fine, it is polynomial, we are ready to accept such algorithm. But the thing is that as of now, no one come up with a polynomial solution for that. The only algorithm available is something similar to the trivial approach, or maybe the exact brute force approach, or something with the running time similar to that. And there are other categories also, like approximation algorithm, those things are there, but what we are talking about is a deterministic algorithm, so normal algorithm. Okay, it's not approximation or randomization algorithm. We are now looking at only the straightforward deterministic algorithms. Okay, and are we able to come up with a polynomial deterministic algorithm for this maximum independent set or maximum click problem? The answer is no. No one come up with such an algorithm. And what about in future? That we don't know. So in between, is it NB? That is the next question. NB means, shall I approach it in a non-deterministic way? So instead of a single CPU. So can you tell me what is a brute force approach for maximum independence or maximum click? By default, if you are looking at a single vertices, that is going to form a click or independent set, right? But when there are more than one vertex in the set, you have to check whether there is edge or whether there is no edge. When it comes to click, I want edge between every pair. When it comes to independent set, I don't want edge between every pair. So that checking you can do, right? So that will take some polynomial time only. But the thing is that how you will enumerate, right? See, if I have n vertices, how many subsets are possible? There are 2 power n subset of vertices possible. So the only approach available now is something straightly brute force or near to that brute force. So let me just tell you the brute force approach, which is very straightforward. Take each subset and check whether it is a click or not, and keep on doing it and find the one with the maximum size. Okay, that will give you the maximum click. And variations also you can think about. Similarly, independent set also, take all subset, and you can start from the bigger subset, and maybe if there are n vertices, null set is there. Okay, that you can eliminate. Singleton sets are there, 2 element sets are there. So always better to start from, as it is a maximization problem, you can start from if I have a 5 vertex graph, they just check whether the graph is going to contain a click of size 5 or independent set of size 5. If no, just go for the checking click of size 4. So that time you have to consider all 4 element subsets. If there are n elements, NC4, that many 4 element subsets are possible, that you can verify in that you can do that checking. That verification is basically when I am giving you a subset of vertices, you are just ensuring whether there is an edge between every pair of vertices or not. Okay, that you can do in a polynomial time. Okay, so that is speciality of non-deterministic algorithm. NP means the verification should happen in polynomial terms. That is very important. So hope please take the lecture notes. I am explaining many things which are there in the slides or which are not there. So whenever you are finding something interested, please note down. So these things I am just repeating only because in the previous video also I discussed when it comes to non-deterministic polynomial time, the running time of the algorithm is polynomial when in a non-deterministic settings. But the verification, given any subset, checking whether it is a click or independent set, that checking you can do in polynomial time. That you have to make sure. Okay, that's all that we can do, right? Because given a subset of vertices, just check whether every pair, like if there are n vertices, n square pairs are there, check whether there is an edge or not by looking at the adjacency matrix. So it will take some order of n square time only. That about the verification part. But what about the final running time? For every subset you have to do this verification, so it will take some 2 power n like that. Okay, so and slight reductions are also there, but all our current best algorithms is running in exponential time only for both the problem. So what is the conclusion is exponential in a deterministic settings, but instead of that, if I have that many processors, I can execute all of them, because let one processor check all one element subset. Okay, I can assign that task to one processor. Parallelly, let another processor check the possibility of all 2 element subset, and the third one let it check all possibility of 3 element subset. Like that you can proceed. Yeah. So the concept of max click maximum independent set, these things are clear, and it is I hope you understand they are both inherently difficult problems. Okay, but the question is, for the time being, it could be difficult, but in the future, can anyone come up with a better algorithm, deterministic polynomial algorithm itself? Okay, the answer is, again, we don't know. So there is no lower bound theory proof even available. At least you can close that problem in that direction. Like in the future also, it's not possible, but it's not stopping at that point because we don't have a proof. So we are it's a like a open problem, or it's a question mark at that point, whether it will reduce to p or not. Okay, so in that way people started thinking about the reduction between difficult problems, if that is the case, in the benefit of reduction also, if I got a polynomial solution for one of the problem, every non-deterministic problem become deterministic. Okay, deterministic by default. If I'm saying polynomial, I mean deterministic polynomial time. Okay, so that is a default terminology. Now let's see how these two difficult problems are related to each other, and how they are how I can reduce from one problem to another. With this example, it is very clear. You can see that for the given graph, if you are looking at the maximum click, this is v1, v2, v3, v4, and the same subset of vertices is acting as a maximum independent set in the complement graph. Now the thing is that, is it true for any graph? Okay, so you can see the same thing is acting as maximum click here, and the complement graph it will be. So it's very, the proof is also very straightforward, right? Because when I have a maximum click, every vertex is connected to each other, and the same thing in the complement graph is going to be completely disconnected, because in the complement graph we will remove all edges which are available in the given graph. So that is going to be the maximum independent set. So in that way you can prove it easily. Okay, and that observation you can prove. So what is the thing is that as of now, both click and independent set problem both are difficult, but in the future, if someone is able to come up with a deterministic polynomial algorithm, easy algorithm for the it's a independent set problem, max independent set problem, you can use it as a black box to solve the max click problem. How you can use it as a, so whatever be the given graph I am having, and I want to find out the max click, or I want to check whether this K4 is a click or not, you just make the complement graph. In the complement graph, you check whether the same subset is making an independent set or not, because you already have a polynomial algorithm for that. So what I done is, from this problem to this problem, I have a reduction. And what kind of reduction I am having? I am having a polynomial reduction, because from a given graph to find the complement graph, you don't have to spend beyond polynomial time, right? In the sense, what you have to do, keep all vertices as it is, just look at the adjacency matrix, you just flip that 1s to 0 and 0 to 1s, that's all. If I have an edge between a pair of vertices, there will be a 1 in the adjacency matrix. Okay, if I have a 0, mean there is no edge. So wherever I have a edge, make it no edge, make that 1 to 0. Wherever I don't have an edge, like this v1, v5 and v3, v5, give an edge by flipping that 0 to 1. So that's all. So that is just if there are n vertices, n square entries will be there in the adjacency matrix. It is just a order of n square flipping of 1s and 0. So in that way you can you can just find the complement. So once you find the complement, you just run the polynomial algorithm. Assume you have, as of now, both are difficult and you don't have a polynomial solution for both, but in the future, if someone is able to come up with this what I can tell, polynomial solution for the click problem or independent set problems, this reduction is bidirectional here, so you can go from here to here and here to here. If I have a easy algorithm for max click, I can use it as a black box. You know what is that concept. I have given many examples to solve in max independent set problem. If I get a deterministic polynomial algorithm, easy algorithm for max independent set, you can use that as a black box to find max click. From one problem to another problem instance, the times I have to spend is just polynomial only. Okay, this is reduction. Okay, similar reduction, but how to do this reduction is something, the real task. So the problems may be from graph theory, number theory, etc., and from different domains you will be getting this NP problem, and how we can find this reduction is what people are interested, and it is something like you have to analyze many factors, and it is not so an easy reduction actually. So by observation also you can't say. This is a simple example, so that's why you are able to follow this, but in general coming up with the polynomial reduction from one to problem, it's not so easy. Okay, and you have to make many observations and you give a rigorous mathematical proof saying that your reduction is correct. Okay, and Okay, this is what I was trying to say. So I have a reduction procedure by which I'm reducing the click problem instance to an independent problem instance, and particularly say I have a graph and I'm trying to check whether the graph contains a click of size k. Okay, and this I am asking on a complement graph of the given graph. So where I am asking or I am trying to find out a what called independent size of set size k. Okay, so if I have s for this instance, I can say this also s, and checking for yes or no as well as this reduction, both are taking polynomial time, so this can also be solved in polynomial time. So the reduction must be a polynomial time reduction, so that is very important here. This g k, I mean a graph, and I am trying to check whether it is containing a click of size k, is an s instance if and only if g complement k is also an s instance. So in the complement graph, if I have a independent set of size k, if the answer to that instance is yes, the same gk, that instance is also going to give you a s answer. Okay, so I hope this statement is clear. So here some of the mapping is given for the graph g1, some random graph. I am trying to see whether there is a click of size 3. This is one instance to my algorithm, and I am mapping that to g1 complement and asking for a independent set of size 3. So like that. So here some random mapping is given. So from some other graph also this same instance may be mapped, because okay, yeah, so something like that. So this the correct mapping is like from g to g complement, and k you have to keep as it is. Okay, so that's all. So the consequences of the above reduction is, if independent set is I mean the right side of the reduction. So typically from here to here, if I have a mapping like this is found to be tougher, but in our particular example there is mapping like this also, so you can have this reduction, but sometimes the reduction may be in only one direction, that is that the people are able to prove it, but may not in the other direction. Anyway, so the if with respect to this particular reduction, if I got a polynomial easy solution for the hardest problem, say an independent set, definitely click is also easily solvable, say class B. Okay, so that is the benefit we are having. And accordingly, if I have a look at every problem, say in NB, like I explained in the last video, and I have a reduction to a particular problem X, it can be any problem, as I already told you that Cook-Levin the satisfiability problem is the right candidate to start with. Okay, but anyway, so if I have a reduction from all NB problem to a particular problem, I can say that this is and the reduction means a polynomial reduction, that is important. This is hardest among all NB. Anyway, all these are hard, this is also hard, and this is hardest among all these. Okay, so I can call it as an NB hard problem. Problem X is said to be NB hard in and here, I mean, with respect to this mapping, this X is said to be NB hard. So in addition, if problem X is NB also, because we don't know when I have a mapping like this, as I already told you in this one, you refer the previous video. So this is set of all NB problem, and from every instance I am having a mapping to a particular X, and this X can be inside or outside. So if I have a reduction like this, this is just NB hard. But if it is inside like this, okay, so that means it is this area, it is NB hard, because in the sense I have a reduction from all NB problem, and at the same time it is NB also, and this portion is what I can call as NB complete, and this outside portion is just NB hard but not NB complete. For the problem to be NB complete, it should be NB also. So what is an NB complete problem? It is NB hard plus NB is what we can call as an NB complete problem. So that is written here. Okay, diagram, given a clear diagram in the next slide. So I am removing this. So in addition, if the problem is NB also, I can call it as NB complete. So the definitions are very important. Understand it in the right sense. So what is the advantage of this reduction? If we discover a deterministic polynomial time algorithm for one NB complete problem, in the sense all are mapped each other, right? So if I am getting something for one NB complete, because from every other problem I have a map into this particular problem, then P become NB. So that is what we are interested, and as I already told you, it is a $1 million question in the theoretical computer science, and people are not able to prove this, whether a P equal to NB, whether or P is a subset of NB, anything if you can prove, that is fine, but there is no proof available in both direction. So it is just an open problem. If someone is able to solve it in any direction in the future, so you will be getting some $1 million. So like that so that much important is this problem, because many people tried it out and they couldn't find. So those who are getting a solution, it is something a breakthrough in the field of theoretical computer science. Okay, Now to show, now given any random problem, say y, so just like what we saw in the previous slide, say independent set problem, something, how can you solve that it is NP complete? Okay, so you may be thinking to show a particular problem, say x is in NP complete. First you have to show that it is NP hard, and then you have to show that it is NP. Okay, you can do it in any order, but checking, just proving that it is NP, it is mostly straightforward, because you just have to make sure that there is no deterministic polynomial algorithm available, and at the same time the verification of a particular instance should happen. So that part is important in polynomial time. So given any random instance, say by the brute force approach, the verification should happen in the polynomial time. Then I can call this particular problem as NP. So that problem part is, I mean, proving problem is NP is mostly straightforward. We have many problems listed in that category and proved in that category. And what about NP hardness? That is something tricky, because from every problem you have to do a mapping to this particular problem. Is it possible? Right, it is not possible, right? Because thousands of natural problems don't be NP complete in computer science, biology, economics, etc., and there are around 5,000 problems. This I taken from a some article, and this might have increased right now. Okay, so that about it. It's an approximate. So this is a big set, right? So how I can take each and every such problem and give a reduction to particular problem which you are interested to show that it is an NP complete problem. Okay, some x you want to prove that it is NP complete, and this is a way. And this is not practical at all, but we have a shortcut actually, because the first reduction is someone already done for you. Maybe it's definitely it is a very difficult task. I mean, he might have taken all NP problem, or he given some general framework by which any NP problem could be mapped to a particular problem. Okay, so definitely such a proof is already given by Cook and Levin, as I introduced this in the previous video. Okay, so they come up with the first reduction to a problem called circuit satisfiability. Again, these things we discussed already. I just tried to define what is this problem. So before coming to this video lecture, please watch the previous video systematically and come to this. So you might every terminology I am explaining will be clear to you. Okay, so satisfiability problem is something, the very first NP complete problem that is already proved. Now for a given problem, and from this satisfiability there are some unknown to be, I mean, in the next video I am explaining that again, the carp reduction, where he might I mean, from this circuit satisfiability there are problems like formula satisfiability set, vertex cover independent set, like that. Some around some 21 reductions happen in the initial phase, and later on many people added many more reductions. So now this NP complete set itself is bigger. I mean, we have NP hard as well as NP that prove for many problems. Okay, so for a new problem which you are having, you might encounter in future, say some other branch, maybe some other domain, it may be biology, economics, from anywhere you can list problems. So problems are already listed, and you want to show that it is NP complete. It is very easy for you. It's not so easy, because you have to find a candidate problem. Okay, something which is already proved by someone else as NP hard, and take that problem and show a reduction from that to this. Okay, so what I was trying to say, let me remove these things. I have a new problem, say y, and I want to show that this y is NP hard. First thing, NP is straightforward. NP hard and NP complete together makes it NP complete. Okay, so it is enough to have a mapping from x to y. This is what I am trying to say. So already from all problem I have a polynomial reduction to x, and from x I have a polynomial reduction to y. Says that polynomial to polynomial, from all problem I can reach y. So this is the concept. Okay, so whenever you are getting a new problem and you want to show that this new problem is NP hard, take an already proved NP hard problem that is proved by someone else. Okay, so already, I mean, if you want, you can add a third problem also. Say now you have some z also with you, some other z, and you want to show that this z is NP complete. It is enough to give a mapping from y to z, or you can give a mapping from x to z. It's all up to you, because whether it is x or y, we already proved that it is NP hard from, because of this these two set of mapping. So for a z you can either go from x or you can go from y. And if you are going from y on polynomial time, again polynomial time, again polynomial time, so altogether 3 polynomial time will add up to a polynomial time. So this is also a polynomial reduction. So this is this much easy, right? So take any candidate problem, but the problem which you are selecting as x, which is already proved as NB hard, should possess some similarity with the new problem you are having. Then only you can do this mapping, because in the independent set problem we chosen that click as the candidate problem, and from click we shown that reduction. Similarly, in graph, Metascover is there. There are matching, like that many problems are there. So candidate problem from the same domain you have to choose. Maybe from a different domain also, and that identification the problem is something that matters, okay, and also how to show that reduction. So this is not an easy thing, but many reductions are already available, but in future also many people are parallelly working on this, and you can also come up with a study on this if you are interested, okay. So that might be your PhD work and all. So maybe your final thesis and all will be few steps, but the hard work is spent behind is something huge, okay. You have to study all similar problem, and you have to find a candidate problem, and from that problem you should give a rigorous mathematical reduction from that problem to this, and you can prove that it is also NB hard, because I have a reduction from an already NB hard problem to this problem, plus it is NB, saying that it is NB complete. Hope the idea is clear. So this is the final conclusion I want. So from the first video lecture onwards, this is 5th video, right? So go through all the previous video, you will get the clear idea. So initially we classified problems, computational problems, into 2 category. Polynomially solvable, by default p time, in the sense deterministic, okay. So by default, if I'm saying polynomial time, it is deterministic polynomial time only. So the initial classification is like a polynomial solution and exponential solution, and we have certain problem like which are having inherent an exponential behavior, like enumerating all subsets or enumerating all spanning trees of the given tree. You can put under this category, okay. Now in between we have the problems for which we don't know the the complexity status so far. Say deterministic polynomial time algorithms, and there itself some are deterministic polynomial time and some are non-deterministic polynomial time also, and we are interested on this non-deterministic polynomial time, which are hard in the sense there is no deterministic polynomial solution available for them, and there we have this classification like NB hard as well as NB complete, not classification based on the reduction, okay. So this is the current, again I can say that it is just a belief, a set of all NB problem, and this P is found to be a subset of NB. I explain why it is so. If I have a mapping from all this NB problem to a particular problem X, if it is outside this NB, so this is a full NB set. If it is outside, I can just call it as NB hard, and if it is NB also, I can call it as NB complete, okay. So that's all. So hope you get an overview about these things. Maybe one more reduction we will see in the next video lecture. Yeah, thanks for watching.